Questions? All right, well, as usual, what I'm going to do is I'm going to kind of go through this little presentation and then I'm going to work some selected problems out the back of the textbook. All right, so properties of logarithms. I think most people, if they're kind of algebra oriented, this will be a pleasant break. You don't have to worry about strange things, but there are some properties that mirror what you might have had in something like Math 095. I'm sorry, 097. Because there's this thing called the product rule, the quotient rule, and the power rule, which if you remember back to 097, if you had that, or you would have had it somewhere else, this kind of material to get into this class. There were rules by that name that dealt with exponents. Okay. Well, here we've got very similar rules that deal with logarithms. The first one is called the power rule. The power rule. Now, the way that this works is just like with exponents, when you're multiplying like bases, you add up the exponents. Multiplication and addition have a correlation. Here, the same thing is true. If we have the log of any base of m times n, then we can break it apart addition-wise. In other words, log base m plus log base n. The product of the logarithm of the product is the sum of the logarithms. It works both ways. All right, so let's look at a couple of examples. They picked out these strange bases, and I guess they do that just to show you that it works with any base, but it says log base 6 of 7 times 11, and they're purposely taking two numbers and multiplying them. And then that just shows you that we can break it up into the log 6 of 7 plus the log base 6 of 11. Okay, because they're being multiplied, we can take them and break them apart as addition. Now this one right here is a little bit more realistic because it's got 100x. So remember, whenever you have a coefficient of x in front of a variable, any kind of variable, then that simply means multiplication. So the log of 100 plus the log of x is equal to, well, I'm sorry, so we're breaking it in two. Now, why does this end up being 2? Anybody got any idea? It has to do with the property from last time. I can't remember what they called it, but let's just kind of look at this. Remember, log with no base like centered there. It was 100. What this means is it's the common logarithm. So that's log base 10 of 100. So how does that come about when we're talking about the inverse, when we're talking about as an exponent? So as an exponent, that's what this means. Remember, if there's no index down there and it says the actual log, it means log base 10. We just don't put it there. So since that's the case, then it means 10 to the x is equal to 100. All right. So this would be equal to 2 because 10 to the 2. Remember, the log is finding the exponent that will give you this value. And the exponent is, of course, on this base here. All right, so that's why this becomes a 2, because the log of 100 is 2, because 10 to the second power is 100. So that can be simplified down, and then this one just stays as log of x. Okay, any questions? All right, the second rule is the quotient rule. In dealing with exponents, when you're dividing like bases, you would subtract the denominator exponent from the numerator exponent. So let b, m, n be positive real numbers with b not equal to 1. So the log base b of m over n is equal to, and it can only go in one order because remember, multiplication and multiplication and addition, they're what we call commutative. It doesn't matter what order we multiply in or what order we add in. Same thing happens with division and with subtraction, and this is why these two things are so closely related. Is that the order is important. There's a difference between m over n and n over n. In other words, 3 divided by, well, let's say 6 divided by 3 is different from 3 divided by 6. You end up with a reciprocal when you change the order. Same thing with subtraction. 5 minus 2 is different from 2 minus 5. They're opposites of one another with the sign, but they're not exactly the same. So we say that these are not commutative. So that's why this order is important. So the log b of m, the numerator, minus the log b of n. All right. So let's look at a couple of examples. Log 8 of 23 over x is log 8 of 23, the numerator, minus log 8 of x, the denominator. And then also remember, the natural log has its own little thing here. It doesn't use log base anything. When we first looked at it, I guess they kind of called it log base e, but that isn't used. What's used is L of n, meaning the natural log, but that means log with the base of e. So natural log of e to the 5th over 11 is equal ln e to the 5th minus e to the 11. Now this right here can't be anything done to it, but this is kind of the same thing that we looked at with here. So the ln and the e undo one another. So this is equal to 5. Okay. Again, that went back to a rule that was in that last section. So this right here is ln, well, this is ln and the e undo one another, and you're just left with a 5. So 5 minus ln 11. It's not quite the same as this, but it's similar. All right, any questions? Just stop me if you need anything. All right, and the last one is the power rule. Okay, you remember and I'm reviewing these because they will help a little bit, but the power rule in dealing with exponents is basically like this. If we have a to the n, and let's just say that this was x, and we raise this whole thing to y, then the a gets the y, and then the n gets the x times y. Likewise, there's it still comes within the context of the power rule, but I think they may call it a quotient. It's not the quotient rule because that refers to the one where you subtract the exponents when you have like bases. But if you have x over y, and we're raising it to the nth power, then both of these get the n, okay? And then if there was another power on one of these, then this would apply here. Okay, so just remember that. That's essentially, both of those would come under the context of the power rule. We're dealing with exponents. All right, but the way the power rule works for the logarithm is slightly different. If we take the log of any base of m to the power of p, then we can take that power and put it back out in front and multiply it, and that's equivalent. So the power can come out in front as a multiplier. They sum it up as the logarithm of a number with an exponent is the product of the exponent and the logarithm of that power. Okay. So using the power rule, we'll look at a couple of things. The log 6 of 3 to the 9th power, well, the 9 can come in front and multiply the log 6 of 3. Now, I can't remember if I remind you of this, but in earlier mathematics, and it also comes within the context of exponents, that x to the 1 over n is equal to the nth root of x. And also, we have m over n up there. In other words, if the numerator is something other than 1, this part still happens. Okay. And it can also sometimes be looked at like this. It means the same thing. But this one right here is the most useful. Okay, so in other words, we can take a radical and transform it to a base, and this is what they call the radicand in there. Take that radicand and raise it to what we call a rational exponent. So that's what they did here. See, that's cube root of n. Well, it can be written as x to the 1/3 power. So then when we do that, we can take it as a power and move it up front to multiply. And it doesn't really matter what the logarithm is acting upon. In this case, it's the log of x plus 4 squared. So the 2 comes out in front of log of x plus 4. So let's just sum them up. The product rule, the quotient rule, and the power rule. We're going to use these a good bit. And then also, these things are going to come back into play here because you're going to see those used, okay? All right. So they ask us to expand. So anytime you see something expand, you're going to have like a condensed expression here. And you're going to take it and bring it out as far as you can. And it's going to be longer, essentially. That's why they call it expansion. All right, so there's two things in here, first of all. They're applying the product rule first. In other words, these two things are multiplying there, the x to the fourth and the y to the negative, y to the 1/3. So then that's the log b of x to the fourth plus the log b of y to the 1/3. And then we can take the 4 and move it in front of the log b of x plus the 1/3 log b of y. All right, any questions about that? Something. Okay. Just want to make sure what we're covering. All right, now here's another one. It's a little bit longer. It's got more stuff to do. We've got the log base 5 of square root of x over 25 y cubed. Okay. All right. First of all, we got to convert that radical to x. The square root of x is x to the 1/2 power, because when you got a square root, there's an understood 2 right there. It's just that's the basic case, so they don't put it there. It's just like why you don't see an x to the first power, because x to the first power is just x. So log base 5, then we're going to use the quotient rule because this is a fraction. So the numerator gets to be log base 5 x to the 1/2 minus log 5 of the 25 y cubed. All right, now notice on this one right here that that's 25 times y cubed. So we're subtracting this whole thing. So when we break apart with the product rule, we're subtracting both of those now. So the 25 is 5 squared, and that's going to help us in a minute to simplify this even further. Plus, remember, we're multiplying the log 5 of y cubed. All right, so we'll simplify these in here, and then we'll carry through our negative sign. You could do that first. It wouldn't matter. I probably would have done it first. But anyway, so the 2 comes and multiplies the log here, plus the 3 comes and multiplies this log, and then they carry the negative sign through, minus 2 log 5th of 5, minus 3 log 5 of y, again, because this negative sign is subtracting both. So what subtraction does is it changes the opposite to the opposite sign. All right, so let's see what we got here. So this one, there's not much we can do with it. It's already simplified down. But again, this one is very much like that first one we looked at. Because this is log base 5. Because it's log, hold on a second. So it's 5 to the first power is equal to 5. And how do you see that? Well, because the base and the logarithm are the same. So the only way that's going to happen, remember, if you took looking at it as this, in other words, as an exponent. So let's put the, and again, this is following that rule. This means 5 to what power is equal to 5? Well, x is equal to 1. So we're replacing the whole thing. So this right here becomes 1, so it's negative 2 times 1, which is just negative 2. And then the last one stays the same. Okay. All right. Let's move on. If you don't have any questions about that. All right. So now we can use the rules backwards to condense. Okay. So the product rule works both ways. So we can condense if we like. So we've got log 25 plus log 4. So in other words, let's put it back together into one logarithm. They're being added. So that means we just multiply the 25 times the 4 and have log 25 times 4, which is log of 100. And then this can be written as 10 squared. And remember, the same thing's playing that we just looked at. This is a base 10. Okay. So 10 to the what power gives you 100, or 10 squared? Well, it's that little 2 right there. Because the 10 here and the 10 there, the 10's not here because, again, this is what we call the common logarithm. So it's the basic case, so they do not put it there. But it's understood that that's a 10 there. So the 10 here, the logarithm base undoes that. And so all we got left is 2. So this one is the log of 7x plus 6 minus the log of just plain old x. And again, these are common logarithms, all base 10. That's what that means. So these go in the numerator and that one goes in the denominator. That's really all we can do. Okay. So second, 2 times ln of x plus 1/3 of ln x plus 5. All right, that's what we're converting. So the 2 is going to come up as a power, and the 1/3 is going to come up as a power for x plus 5. All right, now this is a plus, so we can multiply those two as one logarithm. Remember, the ln is the natural logarithm. So the natural logarithm of x squared times the logarithm of x plus 5 cubed. I'm sorry, 1/3. And then this can be converted back to the radical. Remember, that means x plus 5 to the 1/3 means cube root of x plus 5. All right, the last thing is called the change of base property. The change of base property is very useful because it can help us solve certain equations when we want to evaluate them, essentially. If we have essentially and I shouldn't say an equation, it could be part of an equation, but we have an expression. And one of the things you might notice that on a standard calculator, scientific calculator, they only have the ln and the, where's the ln at? Well, they have the common logarithm, which is base 10. I know it's on here. Do I have to pull it out from? Well, I thought it was on here because I've done it in my, oh, there it is right there. Below the, it's just that you can't see it until you make it big. So there's the natural logarithm. That's the only two that you got on most standard calculators. Now, the big computer graphing calculators that have so many things and things are all buried. Well, you might be able to get it, but for most basic calculators, and especially back in older days before calculators, the only thing that people had was like a chart in the back of the book that would give you a bunch of logarithmic values for base 10 and maybe for the natural logarithm. So since that's all you had, then you would take advantage of this. But anyway, that's neither here nor there because we got those on the calculator, but generally we've only got those two. So anyway, if you have the log base b of m, and like I said, b can be anything, then you can convert it to the base of your choice. And most likely the base of your choice is going to be the natural logarithm or the common logarithm, base 10. So then that means that you can take this and take the value that's being sent into the logarithm, whatever base you use, you put it there, and then you put the m in the numerator. And in the denominator, it's log of the same base to the base over here. And they try to give you a word for it, a sentence for it. The logarithm of m with base b is equal to the logarithm of m with any new base divided by the logarithm of the base b with the new base. And it works, of course, for common logarithms and natural logarithms, because those are most likely the ones you want to use because those are the most readily available on the calculator. All right, so to convert this to logarithms, we're going to convert it to the common log. So log 7 of 2506 would be just the common logarithm of 2506 divided by the common logarithm of that base of 7. So anyway, let's look at this. So put that in there. Then I'll put 2506 divided by So you got to be careful with calculators, and that's why it's always a good thing to write down things. All right. Let me take that. Maybe I did put that in. 7 logarithm. Put it in there. And then 2506 logarithm divided by 4.02. So you see how it comes about there that they get that value. And you can also do it to logarithms. You know what? They're using the exact same one. And just to show you, it doesn't matter which one of those you use. You can even do it to base 3 if you wanted to. All right. But like I said, is the reason why you convert into common logs and natural logs is because those things are most readily available on a calculator. All right. So 7. And I'm going to make it big to see the natural logarithm. Put it in the memory, and then it's 2506 divided by, and I want to recall that thing, 4.02, no matter which one you use. All right, any questions? All right, let's see here. Again, let me see. Got so much stuff stapled together here. All right, this is what we'll see. All right. So let's go over to our board and look at some things. All right, so y'all are don't questionless. So we got a log. Oops. And it's base 9 of 9x. Okay. Let's notice something. See if I can bring up that book in case I need the instructions. I don't have all the instructions here like I have. Oh, this is it's actually the same thing. Okay. All right, so we're going to expand this one. So there's a multiplication in there. So we're going to use the addition rule. So log 9 of 9 plus log . All right, now this right here, remember what the logarithm is? It's saying what do we have to raise this base to get this? Well, it's 1. So anything like that you can simplify, you do. And so there's the final outcome. Okay. So back, if you're keeping up, this is number 4 and back of the textbook. All right, so fraction. So we're going to use the quotient rule. So this is going to be first ln e to the fourth power minus ln of 8, the denominator. We're subtracting that out. Now, are we finished there? We can kind of use the power rule here to put it in front. All right, and remember ln, or if you have any base, I'm sorry, if you have any logarithm and you, and this would be like the common logarithm, and we just kind of looked at this here. See, it's the same principle here. This is logarithm base e, so the e's undo one another. So the same thing is going to happen here. We're going to get a 1, but we got a 4 multiplying that one. Oops. So there we go. That's as far as we can go as far as expansion. We all right? Well, let's look at some with the power rule. Or what, yeah, at least one here looking at the power rule. We used a little bit of the power rule already, but this one's going to have a little bit more. Okay, so ln of the 7th root of x. Remember the rule here to write it as an exponent. This is going to be ln of x so the 1/7 comes out in front, and it's just 1/7 ln of x. Okay. All right, so let's look at one where we can expand to everything here. All right, I'm going to put this one up here, and I'm going to give you a few minutes to look at it and see if you can do something with it, and then I'm going to come back. So the common log and then what I want to do. Okay, so look at that one, write that one down and see if you can and this is actually, you know what, I messed up here. That's actually a 5. It probably doesn't matter within the great scope of things, but in order for it to be like the one in the textbook, it's a 5. My handwriting is not. Write that down, see if we can do anything with it. Oh, textbook right here real quick. And I'll put it back in a minute. bar down here. All right. So let's go over here and look at this on that board. All right, so we're expanding. So the first thing it's smart to do is do this. So we're going to write it with that rational exponent of 1/5. All right. And then that 1/5 will come out as a multiplier. For this whole thing. Probably not really needing that parentheses out front, but I'm trying to be safe. And then we're going to use the quotient rule because that's a fraction. Now here's where the parentheses is going to be really important. Okay. So it ends up being 1/5 the log of x minus 1/5 log of y. Let's see. All right, let's do one more way up towards the end of the section. Oh, I'm sorry. You know what? This has got different rules. So let's yeah, I didn't have it written down. Let me write those different rules. All right, so what we're going to get one that's already expanded out. So that's a y. All right, so what we're going to do is multiply the thing through to both of them. So we got logarithm. Well, I'm sorry, we're going to multiply it in a bit, but what we're going to do is It's already multiplying, but what we're going to do is put these together as one logarithm with the quotient rule. So that's just x over y. Which is equal to, and then this is going to come up as a power. And then we can change it one more time back to a radical. And this is the square root, I'm sorry, the cube root. That's 1 over 30, of course. All right, so that's it. All right, so let's let me come back and do another one of these if we have enough time. Let's see. I want to do the change of base property. So in other words, so I want to all right, so let's say we got this one. And I got log base 6 of 17. And the reason why I wanted to jump to this so we make sure we finish it is because this is very handy, as you're going to see, especially in the last two sections. Very handy because if you got a different base. So remember, the change of base is the numerator is going to be the log of the main value input, and then the denominator is the log of the base. So I'm just going to use here, I'm going to use logarithm, the common log. All right, and then when I'm putting the squigglies because this is an approximation now. It's 1.2, and just to show you how I'm getting it. Remember, 17, and then you hit the log, and that's 1.23. Oh, 45. All right, so and then 6 logarithm. And it's a good idea to write them down because if you hit something wrong on the calculator, You're not going to be able to get them back without doing the calculation again. But let me just show you. I'm going to put that one in the memory. And if this is generally the best way I know of to use a calculator to do this, put that in the memory, then put in the 17, hit the logarithm, and then divide by the memory recall, and see we get approximately 1.58. What is it? 5812. Okay. Okay, I'm gonna do another second. I'm gonna do one little thing here on the side here. Hold on one second. Be right back. I just wanted to look at something here. Okay. Sorry about that. All right, so let's do another change of base. All right, so here's a strange base. It's log pi. I wanted to use this one because remember pi is an irrational number, like just like the natural logarithm, and you could use the common logarithm, it's still going to work, but I'm going to use the natural logarithm here. Okay, so again, the change of base property is the log of the input up in the numerator and the log of the base in the denominator. All right, so let's see what the Mr. Calculator says, because we really need that for this. course, I got to expand it out to get it. So I'm going to put that in my memory. Oops, wait a second. Wait a second. I messed up. Okay, so it was, you got to do pi first. For the, as far as the calculator is concerned, you really need to have that already done, unless you got a calculator that lets you put in parentheses. All right, so there's the log, the natural log of pi. All right, and then the other one is 400. So I'm going to take that and divide it by. All right, so what it looks like is 1.4473. And here's the funny thing about it. If we did the natural logarithm, it would come out to a different numerator and denominator, but the ratio would stay the same. So again, there's no wrong way to do it. Oops. Did I write it down? Let me do it again. I might have wrote the wrong one. Let's see. Hold on a second. I think this goes down here. And this is why I guess it is. The reason why I'm writing them down is if I do something wrong in the calculator, I've got the values to double check, because everything really needs to be double checked. All right, so let me go ahead. So this one's going to be erased. All right, so it was pi, natural logarithm, and that's the 1.144 thing. And that's what I got down there. Now the 400, I want to see what that is so I can write it down. And that's the 5.99. What happened to it? Well, 5.9915. Okay, so anyway, so with the 400, natural log divided by the member equal is 5.23. And it would come out the same exact, well, not exact, the same approximation. You wouldn't be able to tell the distinction on your calculator. There we go. All right, so I was going to try to do one more, but I don't know if there's enough time. I was going to try to do another one of these. I'll write it up here. An expanded one. I'm going to do it real quick. We got about. All right, so what I'm going to do is the same thing I did on this one up here. I'm going to combine those. All right, 1/3 times that one's put together now into 1. And then this one is going to be plus log 4 x plus 1 all squared. All right, now we can kind of put this together a little bit better as I should have put this up here, but anyway, we'll do it in the next step. All right, now are we finished? Well, no, we're not, because there's a plus here. So we can put these together as one single using the product rule. And it's going to look kind of messy, but that's what it is. It's x over y to the 1/3 plus x plus 1 . I'm sorry, it's times, not, I don't know what I'm doing. I'm trying to rush again. And then we can do one more thing here. This is x plus 1 squared. That right there. I'm going to put the x plus 1 in the front. And then, oh, that's a terrible one. I said, I hate to get rushed here, but. And then I'm going to put the cube root thing. Remember, I'm changing it back to that. So it's a single logarithm. So there we go. All right. Like I said, I wanted to have one long one. All right. So that's pretty much it for today.